Thank you for all the attendees, and then I understand this is being recorded, so for everyone listening later on. And Joel, if you want to start sharing your screen, I'll do a quick introduction. I'm Ari Kaplan, Global AI Evangelist with DataRobot. Been here for a couple of years, and before that, spent many decades as a data scientist. Actually worked with the Philadelphia Phillies and many other professional sports organizations, helping create both data science and analytics, but also doing some of the humanistic behavioral science studies and how they merge. Towards the back end of this, I'll kind of swing back to that topic. But Joel, do you want to introduce yourself?
Good thing. Yeah, I am a customer-facing data scientist at DataRobot. Been at DataRobot for about 7 months now. Scientist at a consulting firm. My background is in mathematics, a lot of heavy sciences, and then found data science through the application of snow. So I currently do some snow research as well, and that's kind of how I fell into this field. Yeah.
Well, excellent. So you were, and Joel's going to talk, a lot more in depth on, the unstructured and structured data analytics. But, traditionally data science was looked at how you can process structured data, tabular information, kind of what you would see in a spreadsheet, or everything from, numeric information to categorical. And that was great, but there's been an explosion, an exponential growth of unstructured data, everything else, text, image, audio, visual, video. And it's been a challenge to take that information, extract actionable insights, and do multimodal analysis. How do you take actually all different types of data sets and be able to glean information? So, a couple of things happening here. One is the great growth of data that's unstructured and structured. These are untapped assets that companies have that are extremely valuable. They can help, everything from better understanding their customers to, better understanding, predictive capabilities. How do you segment people? How do you find social, sentiment analysis? And what's, so here's kind of the general outline. What is unstructured data? And then, some of the common techniques: natural language processing, GeoSpatial image, some proprietary, some open source, multimodal. DataRobot, where we are, makes a lot of it, kind of out of the box and easy and accessible for both data scientists and non-data scientists. And then I'll come back in and give some pretty fun and exciting real life use cases in sports in this case, and how that's really taking a hold. Then if you go to the next slide, the growth of unstructured data, at first it was pretty much all structured, since that's what you could analyze. But IDC IDG is saying that unstructured data is doubling roughly every 18 months, kind of like the Moore's law, where microchips were doubling in speed and halving in size every 18 months. And IDG also says that next year, 93% of all data will be unstructured. And here's just a kind of a snapshot of different ways of unstructured data. Email, so that's kind of largely text, medical records, text and imaging, which brings up a point of, how do you secure this unstructured data? Documents like PDF and Word, images, geospatial, audio, video, Internet of Things, so sensor data, and how all of it interrelates is kind of the next level. So it's incredible assets, but traditional data science kind of makes it pretty hard to extract and make features out of it. So if you go to the next slide, which is my final one until I'll pass it to Joel, is exponential growth. So this shows you that exponential going up, and kind of one of the teasers to this webinar was former Google CEO Eric Schmidt said from the very beginning of humanity up to the year 2003, there were 5 exabytes of information for the entire history of humanity. Cave drawings, the ancient worlds, libraries, up through all the computers through 2003. That's 1/200th of a zettabyte. And then fast forward only 9 years later, the first zettabyte of information came out. And then 1 year after that, you are able to do the same amount of all of humanity every 2 days. So imagine that all of human knowledge, every 2 days you're adding on to it. So huge growth. And then on the right, we talk about structured and unstructured, but there's a couple in between, semi-structured, where there's information that appears to be having a pattern, so you could analyze it, like XML files, and then quasi-structured, clickstream, things like JSON, where each record might have different types of data or different lengths of data. And so just even interpreting as data comes in, what the format is, kind of ranges in that increasing growth and increasing complexity. So with that, let me, that was just the intro. Let me hand it over to Joel, and then I'll see you in a little bit.
Yeah, thanks, Ari. Yeah, thank you for the introduction. Yeah, as you mentioned, the growth of data is increasing exponentially. And so organizations are trying to think about how it is that they're going to wrap their heads around this entire data. How are they going to manage it? So there was a survey that was conducted of 300 plus IT leaders. And out of those 300 IT leaders, these are the results that they found when they started to ask them questions. The first one, of course, was, the costs of unstructured data and what they anticipate to spend in the future. And you can see there that 65% of those organizations are intending to increase their budget. Because, as Ari explained, the data just continues to grow. And so having to grow their budgets to handle that is absolutely necessary. 50% of them have stored data in mix, right? On-premise and cloud-based. Nowadays, you no longer have things just sitting on your computer. They happen to be on your computer, they're on your email, then they're back on the cloud. And so trying to access all of this data poses a lot of issues, right? And then, of course, 62% of them plan to spend more on storage next year than they did in the following year. Now, this was a survey that was done prior, but you can imagine that the following year, 2022, is going to be the exact same thing, or probably even more money will be spent. But before investing in more storage, a few things that organizations have to consider is it necessary? Ari mentioned that a lot of that data is unstructured, right? Not only is it unstructured, but most of that data is actually just stored and sitting there and not being used. So a lot of analytic tools have been developed to be able to access that information. And so before spending money on storage, we're going to see a lot of IT organizations spending money on analytics tools to be able to analyze that data, right? We know that most of the data is cold, and that data doesn't cost a lot of money. The money is spent on the data that's being moved, right? All the data that's being managed. And the goals and challenges for next year, big goals that would be avoiding large costs is what they'd like to do, better visibility of the data that they have, and tagging for future use, which includes manual labor. Now, these are the types of things that the IT organizations are considering with respect to this survey of 300 plus IT leaders. However, it always comes down to the fact of data usability, right? So we know that a lot of the data is not being used. So one of the things that we have to address is it usable? Unstructured data on its own has a lot of great context. However, it's not quite usable, right? So we have to format it into a form that allows us to leverage it. So there's a few things to consider when you're looking at usability. The first one is the availability of data. We know that unstructured data is plenty available. We know that there's a lot of it. And this just happens to be the extent to which data is currently available to use for the specific problem, right? Also, the relevance of the data is something that we must consider. If you have unstructured data, we have to consider whether or not it's actually applicable and helpful for the task at hand. And then, of course, the completeness, the breadth, depth, and scope for that task at hand is also the consideration. On the right side, I like this Venn diagram. It was pulled from this paper that you see here at the bottom. But you see that unstructured data and big data analytics causes a lot of issues, right? Where we have a lot of data, but it's unstructured. So doing big data analytics, it causes some challenges. Versus if you have unstructured data and data usability, for example, has the context that you like, there's some conflicts that occur. In essence that, yes, the information is there, however, it's not in the proper structure so that you can leverage it. And then the sweet spot is going to be here where you have big data analytics intersecting with usability, and then this area where there's unstructured data, right? The other opportunities happen to be structured data, which a lot of us have worked with before in the past, if those of us are in data science or any field similar to this. But this is what we're going to be talking about today. So the structures of data, right? Unstructured data is considered to be really no structure. GeoSpatial is probably the most complex of them, I would say. So I'm going to talk about the different types of data structures that exist and the different ways that data is stored as geospatial data, and how we provide some structure to it. The first one here that you're going to see is that geographical tables. And that's the table that you see on the right there. And they can be thought of as tabular data in a spreadsheet where, one of the columns is a record for geometric information, such as here in this case, this column pertains to the geometry of the boundary of each one of these locations, right? Traditional databases don't usually house this type of information, and I'll talk about that in a second. But what we can do with these types of databases is then we can then start engineering different features. For example, the centroid of a point, right? If we want to determine the center, now we're starting to featureize. So when I talk about features throughout this presentation, this is what I'm referring to, is how we're going to then leverage tools and analytics to be able to generate more information with respect to a specific input. The other type of data is raster data. And raster data we've been familiar with. It's essentially images where we're looking at pixels, pixelated imagery. It's extremely convenient. Why would somebody want to use raster data? It's a simple data structure with cells and dimensions where each cell is uniform. It's a really powerful format for advanced spatial and statistical analysis. It also is able to represent continuous surfaces, and we can perform surface analysis on this type of data. It uniformly stores points, polygons, and surfaces, of course. And then one of the great benefits is that we can do really fast overlays. So if we're doing a lot of maps and we want to place overlays on top of each other, this format is fairly kind to that type of overlay. The other representation are called spatial graphs. This is still ongoing research. I mean, most of these things, of course, are ongoing research, but these spatial graphs are essentially graphs that connect locations or objects through space. And in essence, what we can do is we can do some partitioning where we take, for example, in this case, they're doing some algebraic operation onto a graph, which is called the Lagrangian operation. And it allows you to cluster and partition into in this case, they're partitioning them into watersheds, as you can see there. So with that being said, let's go ahead and talk about the different problems that we're going to encounter in analytics. Text, I didn't talk about the data structure because we're familiar with those, and imagery we're pretty familiar with. But the first few things that I want to discuss are this natural language processing and the different problems that we're going to address, the data analytics that are available. One of them is, of course, name entity recognition. We have a lot of text, and what we want to do is we want to go through and identify all of the entities, that is the nouns within this file or this text format here. But not only do we want to identify the nouns, but we also want to classify, is this a proper noun? Is it not a proper noun, right? Is it a name of a person? Is it a name of a city? Is it a country? This would be tasks that are commonly approached for, again, unstructured data. The other one would be to do some sentiment analysis, I already mentioned, where we want to classify a specific portion of text as either being a positive or a negative context. Aspect mining is another thing that you see a lot of in unstructured data, where you have a lot of text and you want to extract the different components that the text is discussing. So in this case, we have like breakfast, buffet, and include ocean. So maybe they're talking about breakfast at the ocean, and you can start to infer what it is that that article is discussing without really having to read everything, but just having a big glance at it, right? One of the things that I will mention is that all of these things that I'm discussing now is essentially taking that unstructured data and now we're augmenting them with more information, which then can be leveraged for downstream analytics. The one that I'm showing you right now is topic modeling, where we, similar to, I guess you can say aspect mining. In this case, we're looking for different topics that the article is discussing. In imagery, for digital signal processing, segmentation is a big problem that we want to attack, right? We want to be able to label every single pixel within an image. How is this accomplished? Object recognition, right? We now have self-driving cars and we want the cars to be able to identify other cars and people to avoid them, right? So we're building algorithms that hopefully avoid a person and add a lot of penalty to this classification versus if a car sees another car, correct? We want to identify traffic lights and so forth. How we do this is all leverage from unstructured data. And even your phone, even when I open my phone, it's amazing. Every time when I look at my phone, it just automatically opens itself. We're looking at unstructured data and it automatically is able to map and featurize that information. In geospatial, we have interpolation techniques such as kriging, right? We have also hotspot analysis that is done usually by doing a moving window over an entire hotspot. And then we can extract metrics like the median, mean, standard deviation of those locations, and they can highlight certain attributes of space and time. And then we also have graph representations, right? Networks that exist. For example, if you're flying from Seattle to Phoenix, what's the fastest route that's not going to, use up as much fuel? Excuse me, sorry about that. And preserve those spatial relationships. Okay. So with that said, I'm going to walk through the 3 different workflows. These are considered standard workflows. I would say that these are not exhaustive, but they're pretty good workflows for NLP. And then I'll also discuss the workflows for geospatial and then some imagery. What you're seeing from left to right, there is, of course, the process. Usually, even though it's drawn linearly, most data science doesn't occur this way, correct? It's usually a spaghetti mess where you kind of move forward and backwards a lot. But this is the idea. In the perfect world, you should be able to move from left to right without any problems. The first one, of course, is of removing special characters or stemming as well. So any characters that do not belong, any non-alphanumerical characters, you want to strip those. If you want to do any normalizing, depends on the context of your problem. Stemming sometimes provides some really great way to reduce the noise of data. However, for other problems, perhaps you want to segment those words further. In this case, what you're doing is you're just taking the words and truncating them such that you're able to classify them together and group them together, right? And then lemmatization is similar in the sense, however, what we're doing is we're taking that word and mapping it to the most basic or the most fundamental word. That is, the word was would get mapped to be, is would get mapped to be, are would get mapped to be, right? Better, it gets mapped to good. And these are different types of techniques where we're normalizing the data. This is, again, what we're doing is we're going through, text is really messy, okay? When you guys start working with text, for those of us who have, know that text, everybody writes different, everybody has different accents that they put into their text writing, or different commas, punctuations. This type of stuff is what we have to do prior to any sort of NLP work that we got to do, is doing that pre-processing. Once you do the pre-processing, you move on to what is called text parsing. The text, even though you've cleaned up and removed all these things, it's still not in the format that a machine learning algorithm can readily accept. The idea is we need to put this in some sort of tabular format. I will say that there are other models that are able to ingest more, I would say, sort of series type of text. However, I'm not going to talk about those in this case. We'll talk about in this structure. What you're seeing is a table that was created. It's a bunch of gibberish that you can see. In this case, we see the text that came before and after a particular label, in this case, perhaps a social security number. I grab the social security number and I grab the text prior and after. I also grab those character starts and character ends. Now I'm starting to establish some mappings between the text and the label. And I want to develop an algorithm that's going to classify all of these labels. right? Again, what we're doing is we're moving from all that unstructured format and we're slowly moving it into a structured format such that we can implement a lot of the modeling and mining techniques that is available. Another way to represent this data other than the table is to represent it as vectors, right? In this case, we see a T-SNE, what it's called, is the algorithm that takes words and maps them into a specific space and into multidimensional space. In this case, they are being projected to a two-dimensional space, but you can see that science fiction tends to fall in this location here. We see that anything that relates to crime novels tends to fall in this area. And that happens because the T-SNE algorithm is designed such that words that often co-occur together are mapped to the same location, right? So if you're talking about a lot of fantasy novels, those are going to happen to fall, or nonfiction novels, you can see that those tend to fall in this area here. These are different representations of words. What we're doing, again, is taking that structured data and representing them in some way that's going to allow our models to ingest them. The other technique that we see a lot is called a graph, word of graphs. Instead of a bag of words where you're just counting how many words co-occur in a particular text, now what we're looking at is the relationship between the words and the words next to them. How many times do they co-occur? And even sometimes you can add direction to these. And we start adding, for example, some more information about our text. These are, again, different representations of them. Once we have our text in a decent representation, we then can move on to doing the modeling and mining. A particular type of modeling is called topic modeling, also known as LDA, or Leighton-Dirichlet allocation. It's a common method that's applied such that allows you to take text and break it up into different sections. And this goes back to words that co-occur together. You'll see sections such as baseball, bat, outs, things like this grouped together, versus maybe you'll see soccer, cleats, net, score, goal. Those types of words tend to cluster together. And that's what we call topic modeling. All right. I'm not sure what, let me see. Well, this is interesting. Can you see my screen, or am I seeing?
Yeah, I can see Leighton-Dirichlet.
Oh, there we go. Yeah, there. Here we go.
I think, yeah, just go to the other tab. Yeah, there you go.
Is that you can see that?
And then make it full screen.
This is interesting. Okay. Sorry about that. I don't know what I clicked on.
Present or something. Yeah. We can just see your speaker notes, which is fine. There you go.
Okay.
Well, still see your speaker notes, but if you go hit the present button near the top.
Let's see. Yeah. Can you still see my screen or not anymore? Did I lose you the screen?
Yeah, just I don't see the screen.
Yeah, you stop the screen share.
Okay. How about now?
Yeah,
That's better. Just make it full screen.
How's that?
There we go.
Awesome. Okay. My apologies for that. I have no idea what I clicked on. I think I have the hyperlink saved on that image for a future reference. I think these PowerPoints are going to be available at some point. And so there's a bunch of links also tied here for the references for anybody who's interested. And I think that's what happened. So once we have the topic modeling occurred, usually what we have is an evaluation deployment. We do some highlighting, syntaxing, such that we are able to have a human come in and interpret and understand and then make action. Human come in and interpret and understand and then make action. Where we move on to the standard geospatial workflows, you're going to see a lot of the similar patterns. Again, this is a linear mapping. However, it doesn't always work that way. Move on to the linear mapping. I will say that in the data storage management for geospatial is slightly different. We'll say that in the data storage management for geospatial is slightly different. Would you mind muting your? I think I'm hearing an echo. Would you mind muting your? I think I'm hearing an echo.
Yeah, Ari, that's yours. I see it. I checked the mic.
Let's see. How about now? Okay, awesome. Yeah. So in this case, what we're looking at is the first thing for geospatial data that's going to be slightly different is the geospatial database. And this is because it supports data types for geometric objects and allows you to store geometric data. While these non-spatial databases known as RDBSs don't support such data. It also allows you to manipulate geospatial data using kind of a SQL-like language that allows you to do things such as measure distances between locations, determine if an object is inside a region. Those types of queries are usually available in our DBSs versus a geospatial database is going to allow you to do these because it does store these objects, right? Once you have your data where it needs to be, now I listed a couple of geospatial databases and non-geospatial databases here for us. You can see that we have, SQLite, Oracle, all the traditional ones, and then you have their counterparts, which happen to have those GIS embeddings within them and functionalities. Once you have your data, what you want to do is you want to determine a reference coordinate system. And now data sets like these, unfortunately, and maps do not come in all shapes and sizes. Maps are not always flat, right? There are some maps that are flat. However, keep in mind that distorts the distances between each other. So if you're going to be measuring an inch in this map versus an inch perhaps on the globe, it's not going to be the same. Same thing if you do any analytics on this globe and you want to map it to this one, you're going to need to be able to have a coordinate reference system that allows you to unify those together. That's usually the very first step that we do. And if you're dealing with raster data, you're probably going to define a minimum size of a cell and then continue to some geospatial and non-geospatial data processing, such as, in this case, we're doing some movie windows. We apply some filtering to them. It can be a mean, average, median, depending on your problem. You're going to have a different type of geospatial and non-geospatial data processing. And then we go through and extract geostatistics. Again, what we're doing is we're taking this geospatial data, which was highly unstructured, and we're putting it into a structure, again, so that we can do some modeling and classification. So we're just representing spaces in terms of values, where in this case, you're looking at the variogram. This is a technique developed by a mathematician in Africa, and it was essentially designed to determine areas to mine. And then, of course, once we have our geodata located in the proper location, formatted correctly, we go through and do our segmentation. In this case, if it's a map, we can segment the map. And you can see in this case that the spatial data that we're segmenting now is just of a room. For standard computer, you're going to have the same thing, data stored either in a data lake or an RDBS, our newer structure. But what you're seeing right now is the step after that is the data processing, right? We're enhancing, refining. In some cases, you might do some upsampling. That is, maybe you start off with a 240 pixel image and you upsample to 1,000 pixels, or vice versa. If you have a high resolution image and perhaps you're limited by your computational power, you're going to have to reduce that by doing some downsampling. Once you do in this case, I will talk that there's some different ways to do downsampling. There's good sampling and then bad sampling. Essentially, what ends up happening is 1 over the resolution is the best sampling that you want to go over, versus bad sampling doesn't sample very uniformly, right? It misses some grids. Here's another example of different types of things that we can do with standard computer vision. We can also apply filters. Doing some sort of interpolation or gap filling for imagery. There are different techniques that you want to apply to be able to close those gaps. If you do a nearest neighbor interpolation, linear or Gaussian, there are fairly many others, but this is a technique in order to enhance and refine our images. Once we've done that, the annotation and segmentation is really important. This is the feature augmentation stage, where we're going to go through and we're going to start creating features. In this case, perhaps I'm going to say this geometric pattern that you see here, I'm going to label that as yogurt, right? This is the most tedious part of computer vision, where we have to go through and manually label things such as this. For this, you will need a really great piece of software, or if those of us who are fairly familiar with Python can develop your own little GUI, then you're welcome to do so. However, there's a lot of proprietary tools out there that allow you to do this really efficiently. And if you're going to be working in the computer vision workflow with unstructured data, I highly recommend you looking into one of these. There are different open source ones that you can look at, but again, they come with their limitations, right? And then once you have all that, you can do the modeling. The modeling can be complicated, right? We can start off with convolutional neural networks such as this one, where you're taking an image and you pass a filter over the top of it, and then you create a new image with it, right? The number of filters determines how many images you're going to create. If you have 100 filters, you're going to create 100 images out of this. And then what you do is you move on to the next stage, which you create a new filter and you filter it again. You do this over and over again until you get to a single vector. And that single vector ends up being your classification for the different categories: cat, dog, boat, bird. Whichever value gets the highest value happens to be that what we're going to classify it at. Architectures for computer vision can be very complex, right? They can run, this is called AlexNet, fairly complex architectures you can see. And then what they're really doing when you're building really deep architectures like this is we're actually breaking down the image into small components. We're breaking it down all the way down to perhaps vertical lines, horizontal lines, circles, squares, no circle. This is what we're doing such that we're able to take this information and crank out a vector that allows us to classify each one of those imageries. This is the nuts and bolts of what computer vision algorithms mostly do. This is, I would consider the deep learning methods, right? And there are other techniques, traditional techniques that allow you to do this type of work as well. However, they have their limitations. So for open source tools that are available, I'll mention a few of them here. NLTK is one that's available that's going to allow you to take your words and tokenize it, develop n-grams, which is perhaps how two words co-occurring together quite often. You can add part of speech, that is, you can tag words as nouns. A tree model or text chunker where you're going to break up the text in order to do some quick searches, and of course, name entity recognition. Spacey is another one that's really good. State-of-the-art speed, incredible for deep, really great for deep learning integration. So if you're going to be using deep learning models, I highly recommend this one. Destructive tokenization for up to 31 languages or over 31 languages, right? And we have that 13 geostatistical or statistical models for those 18 languages. And then PyTorch. This, the PyTorch library comes with some heavy artillery such as BERT, and then GPT and GPT-2, which sound like really fancy things, but they're these really deep algorithms that were trained on many GPUs, more GPUs that any of us can afford. And therefore they provide a trained model that allows us to take text and transform it into that vector so that we can ingest it into the models. I highly recommend looking at these transformers for those of us who are interested in applying NLP. And of course, GenSim is another great package to use and is available and allows you to do a word to vector, that is, take a word and vectorize it, much like what these transformers are doing, but at a much shallower form. That non-negative matrix factor is a technique to break a document up into different topics. And of course, a different type of term frequency inverse distance weighing. In this case, you weight a term as often as it appears. However, if it appears in all the documents, it's not as important, so you do an inverse weight of that. For open source geospatial data, the one that's very, very common, and you can see here is JDAL, called the GeoSpatial Data Abstraction Library. It's an extremely powerful library developed in C, and mostly was developed as a command line tool, but now comes with a GUI. So those of us who need a GUI, we can definitely leverage this. Another platform is called GRASS, Geographic Resources Analysis and Support Systems. This one uses JDAL, so this also uses this library to do a lot of the transformations. And so does QGIS, which was once known as Quantum GIS, and then they dropped the Quantum. And then you have UDIG GIS. This is a user-friendly desktop. And then Spring, which is technically used mostly for socioeconomic and urban planning. And then for image processing, the open source tools, the main ones that most people tend to fall onto are OpenCV is a really great tool. TensorFlow, PyTorch, and Corina. Corina is a specific package or library of computer vision within PyTorch. It has some really great things such as image conversion, depth estimation, color correction, feature recognition, and even do some image filtering. And I believe it even goes through and does some border recognition for us. And then CAFE 2, which is built on CAFE 1, which is just pure C++ and CUDA, and GPU and CPU enabled, that allows you to do some really great image transformations. On the right that you'll see here, this is a hotspot that Data Robot puts out, and which allows you to look at the image processing and identify what areas is the model focused on. In this case, this was a model that I built on to detect smiles, right? And you can see that it's focusing a lot on the teeth. Perhaps if somebody's showing their teeth, it's going to classify that as a smile or not. And the type of models that are usually leveraged for this tend to look something like this. However, I will say that many times keeping it simple is always the best option. And I'll talk about that in a second. Finally, and then please stop me if anybody has any questions. I want to talk about multimodal. So I've discussed these different unstructured data types. We have the text, GeoSpatial, right, that we talked about, the imagery. So I've talked about how we're going to take this data and place it into a vectorized form so that we can then leverage it in machine learning models. But the thing is, how do we do that? There are complex ways and then the simple ways to do this. In the simplest terms, what we're going to do is we're going to take that unstructured text and we're going to vectorize it. We want to represent that as some number, whether we use an algorithm like t-SNE, like I described, or we use it as a graph embedding or a bag of words. We're going to represent this as numbers, and we're going to pass this into a flattened array. In this case, once that flattened array is going to then create us a vector that is going to determine from the note. This is an embedding of that one note. This note is now represented as a vector. We do the same thing for temporal signals, or if we're working with geospatial data, we're going to flatten it, doing some transformations, and then we're going to also represent that as a vector. And as well as any structured data, they get represented as vectors in this case. This is, for example, a Fusion CNN. The code for the paper that develops this algorithm is given to you here. On the right, we have more complex models, but keep in mind, the complexity of the model is really not what's important. What is important is this vectorization process that you're doing. How are we taking that text and how are we representing it? Those are the things that you want to focus on when you're working with unstructured data, right? Because although things that are really complex and fancy, such as these types of architectures are great to implement. And for data scientists, they're really fun to work with. However, when it comes down to business problems and tackling business problems, often things that are not transparent and clear are not the best problems to bring, are not the best solutions to bring to your business, right? We want to have things that are clear and transparent. Here, an image that different ways in which you can construct a swing. Of course, you know, if you're going through and constructing a swing that looks something like this, or the couch, it depends on, you know, what it is that you want the swing for. In this case, if you want the swing just to entertain yourself, then perhaps going through this work of perhaps building this really intricate swing or this whole entire roller coaster is unnecessary, right? Rather, where we would like to do is perhaps build something that's quite simple, maybe just a tire swing in this case, that is actually does exactly what the task requires and doesn't require too much complex. So we want to stick, whenever you're building models, whenever you're doing transformation for unstructured data, consider keeping the task and the transformations relatively easy. Now, there's an example here that I'm going to present where two different models were created. The first model was really complex, and it was created to tackle three different tasks. Versus what we did is we created one small little model that is able to tackle one task at a time. And so we did some analysis with this, and this was done in DataRobot. And when we compared between the different benchmark and DataRobot, that large architecture, yes, in some cases, perhaps in this case, detecting lateral tumors, it was effective. However, when it comes to, for example, this type of data in this case, histological grades for maybe perhaps tumors, how severe a tumor is, it did not score very well, right? Versus the DataRobot model, which was really simple, that single layer outperformed those. So keep in mind that NLP does not need to be complex. In this case, DataRobot does a really great job of simplifying the NLP and creating vectors for you automatically. And Ari is going to touch on that a little bit. There's another example that I want to touch on for natural language processing. And this is the power of two is what it's called. And we're labeling dates in legal documents. Labeling dates is not difficult, right? You can apply regular expression, extract the dates and say, okay, here are all the dates that I found, fantastic. Now, the issue is that recognizing the type of date, that is not trivial, right? So extracting all the dates is not a problem, but identifying the type of date is an issue. So we want to develop an algorithm that's going to identify the date, right? As I said, identifying the dates is not difficult, I'm sorry, but identifying the type of date is. What we want to do is we developed a process that's going to identify starting, ending dates, signing dates, payment schedule, or other. You can develop regular expressions to do this up to a certain extent, but to grab that last little bit, you're going to need an algorithm. And in order for it to be transferable to other types of documents, an algorithm, a machine learning algorithm is going to be much more effective. Okay, so this was implemented again. And the way we did this is we took for each one of the contracts that we had, the text was extracted along with the date. And if it was a sign date, it was placed in the sign date. If it was a start date, it was placed in the start date column. How we represented that information. This is another example of how we're taking unstructured data and putting it into a structure so that allows our algorithm to ingest it and do some really great things. This is I would say probably the most challenging part is deciding how you're going to structure the data. Is going to determine how well your algorithm is going to do. Now, here what you're seeing are the results. You can see that we bumped Data Robot up against BERT and this answer question methodology, right? And BERT is this really complex model that was developed by Google and supposedly it does fantastic things. However, when it comes to tasks such as this one, it's too complicated. A simpler model that was developed in Data Robot, right? And not simple in the sense that it's easy to implement, simple in the sense as the architecture is not complicated, right? But the workflow can't, as I said, the transformations can sometimes be, but Data Robot handles that for you. In this case, you can see that Data Robot outperformed in the precision. There's some instances where, of course, answering question outperformed it better, but you can see the BERT in each one of these instances did not do better than Data Robot, even though BERT is a much more complex and supposedly is able to handle really, really complicated tasks. So when you're developing your models, keep in mind that you want to keep your models simple, but you work on your transformations. Think about how you want to take that unstructured data and represent it in space. I will leave you guys also with this that I want to share with you is if you're interested in CNN for image regression, there was a tutorial that I had put together with these organizations and then was presented at this conference. And it's still available for you. I placed a link here if anybody wants to take a look at that. And it's going to walk you through how to build in Python a CNN like this from end to end, and also do some assessments as far as like feature and understanding. Okay. Yeah. And with that, I'll go ahead and hand it over to Ari.
Sure. Well, thank you. And before you do, there's a question in the chat from George.
Oh.
Yeah.
Let me see. I can't see the chat at the moment.
So
Okay.
what is the comparability between vectorizations of different kinds of data? For example, combining NLP with GeoSpatial, and what's more extreme, the vector version, like scalar, human weight, and height?
Okay, so it sounds like, so when you're comparability between vectorizations of different kinds of data, that is when you vectorize NLP and GeoSpatial, how are they going to be represented and what their scalar values are? Usually when you do vectorization, you apply what is called the L1 norm to normalize the vectors such that they're represented regardless of where they came from. Does that answer the question? And let me know if I did not get the question correct, or if I didn't understand the question correctly. But yeah, that's usually what the technique is happening is we do apply some scaling to those vectors to ensure that they're comparable. Good question. Very good question.
Great, thanks. And keep the questions coming. And then Joel, if you could unshare your screen.
Sure thing.
Kind of take over. Okay. So I'll kind of, yes, great. Kind of take it from here. And again, people, keep posing questions. So I wanted to bring a lot of what Joel had been saying to a little bit life. Sports example, something a lot of folks, kind of resonate well, but analytics has truly changed the way sports has been played. I had the honor for many decades working in front offices, created and led the Cubs and Dodgers analytics departments, but things have changed, and now the explosion of unstructured data like video processing is through the roof. So imagine being able to take videos of Babe Ruth and quantify his bat swing and bat speed and level of plane. could be done all through AI. So you could see, for example, on the left, the merging of structured data, which is traditional Moneyball type of analytics, with unstructured data where the scouts write reports. I think Joel is an elite player. He has a deceptive fastball and change ball combo. AI can take those words and combined with other metrics like how fast he throws, things like that, can kind of guide, is this a positive player or negative player? Or what are the likelihoods that he will go from high school to making the majors, with text analysis of what actual scouts have written. Or you could see in this image, back lacerated, some health information. Is an injury bad enough to be concerned when combined with some of the metrics information, like how fast they continue to throw? And then geospatial. One of the neat things is how shifting is where you position your outfielders is based on geospatial data. And one interesting thing is for DataRobot, all of our customers, our biggest power user was a baseball team, not Humana, not Bank of America, not a retailer like Kroger or Walmart. It was a sports where they did simulations of every player moving, a foot front, a foot right, a foot to the left. And they were able to win what was an estimated to be 8 more games per year, which is like $80 to $90 million of value. Not by getting better players, but by reallocating only with information, no more money, where they physically stand before a ball is hit. And then in the right, you could see automatic featurization of images, things like that. And speaking of shifts, it's been so successful. It took months and years actually to convince players and coaches to use information to reposition themselves. There's a lot of hesitancy and human biases that were in place. Anecdotally, it could be working, and then one ball is hit where they weren't shifted, and it kind of psychologically throws everyone off. But by and large, up through this past season, you could see the adoption of it. And now over half of all balls in play are against what's called a shift, this data-driven insights. So it's really fascinating to see sports change. And then another is, taking video. There are, for example, a free open source package called OpenPose, developed by MIT, not just for sports. It could be for retail, of people walking around a store, anywhere there are humans involved, and it'll show, where their eyes are, their nose, their arms and legs. And this is one application for free, taking a video and representing it in 3 dimensions. So it takes these videos and puts it in 3-dimensional data points. And then you can do things on the left as a picture, see, just measure how high was that leg kick. And then over time, you can correlate that, relate that to, was the pitch successful? And then start seeing what characteristics of human biomechanics tend to be successful or not. And then taking it to another level, you could see like these skeletal dots moving. Are they consistent or not? So this picture is consistent. His leg is a little bit different in height, still consistent on the left image. And then after the pitch, it's still consistent here, still there, but now his back leg and arm and head are all varying after the ball's released. And then the batter on the right, you still need the context of what the data is saying, but for a batter, your swing is going to be different if the pitch is high versus low. So their inconsistency in height might be okay if your bat is swinging to meet the ball. If it's the pitch the same height, then inconsistency is not right. So being able to parse this type of data, half the teams are not even doing this. It's still very new. It's first step is getting the data. The next step is featurizing it into these dots, and then making features of the features. And then at the end, working with the humans to see what's good, what's bad, what's actionable, what's not. And then the other, going across sports is taking.
All right, we do have a question real fast for you as well.
Sure.
In the context of open pose,
Mhm.
it seems like you need multiple viewing angles to get an accurate 3D representation. Are there any known workarounds, or is it a non-issue?
Yeah, so great question. So for open pose, what you're seeing on the open pose, you only need one camera angle, but from that you'll only get, like for example, the batter, only one viewpoint. So you won't get the full picture. So for things like broadcast data, that's problematic. But if you were like controlling your own recording, you would have like 2 iPhones or iPads and record from different angles, and then use, it doesn't have to be AI computation to make it 3-dimensional. So yeah, technically you could do it from a broadcast, but it's even better when you have multiple angles. So yeah, great question. And there's some cool demos if you just Google open pose. Actually, if you Google Danny Malter, M-A-L-T-E-R, he wrote this great article which really brings it to life and has some Python code to sample that takes it to the next step. So yeah, good question. So that example of Babe Ruth looking at his swing is just 2-dimensional. You can extract how fast his bat is swinging, but you lose, unless you have the 2 angles, you lose some other context. So yeah, thank you for that. Yeah, and then feature engineering. Baseball is kind of discrete. Someone pitches, then someone swings, and then if it's in play, a bunch of players run and throw it. But other sports are more complex. So some of the geospatial and polygons that Joel was talking about apply interestingly to sports. The polygon on the right could be, in soccer, how much of the field do you control? Which players are open for receiving? What's the likelihood of the geographic area? So you can see the person kind of in the back by the letter L in Cleveland has a lot of space, but some of the players on the line of scrimmage don't have much individualized space. So how do you do formations? How do formations change? What change in formations lead to a point or a goal or a first down? These are all type of problems you can solve. And then on the left, it's the pattern of running. This blue line on the left is kind of going straight back. The yellow line kind of squiggles to the left and then to the right. And the middle blue line goes back almost like a half of a T. And then you can make features of the features, saying the one on the left is kind of like a straight, the one in the middle is a straight then left, and the one on the right is like a wiggle. And then you can put context. When did this happen? What was the score? And you can just keep getting more and more complex. And then you can call like types of plays, different formations. So that's really cool in feature engineering. Outside of sports, worked with Lenovo, the laptop manufacturer, and they used visual AI to see if the packages on the conveyor belt before it gets shipped were accurately or inaccurately labeled. So instead of having a human doing the extremely repetitive task, like Laverne and Shirley, if you've seen that show, where they're just taking beer bottles off the conveyor belt, or Lucille Ball doing the same thing, the computer or the AI looks, 1 out of 5,000 packages are mislabeled. And at that point, the human comes. So much more efficient. The example Joel gave of extracting dates, or extracting, did these contracts have signature or not? Incredible use cases. You can look at 1 million documents and just flag who's missing their signature, things like that. And then from those lines on the open pose, you can extract things like what's the shoulder rotation, and then you're generating tabular type of insights. What is the swing of the angle needing the swing of the ball? I don't know if you can see my cursor, but on the bottom second from the left, 50% longer if you can instruct the batter that their swing, like the angle they're moving their bat, matches the angle the ball's going in. If it's different, you have to hit at just a point. If it's the same and opposite, you have 50% longer. That's extremely higher odds of getting a hit. And then the last thing is data drift. AI with unstructured and structured data is very good to see what information's changed lately. How big is that change? What context has that data changed? And then, arguably as importantly is not just what data has changed, but is this data important to your model or kind of tangential to that model? And I don't know how we're doing on time, but in 2 minutes, I'm going to go through 2 examples. Data robot platform. This was a Yelp review doing sentiment analysis. And so Joel was talking different techniques like word to vec and stop words and so on. This is looking at what words were positive or negative to a review. And 2 things that pop out, red means it tends to be a positive review and blue tends to be negative, but sometimes there are surprising words that make sense to me now. The word okay in the context of the reviews is actually negative. If somebody wrote the word okay and you look in the dictionary, to me it means kind of neutral, maybe a little positive, but when somebody wrote the word okay in a review, that review tended to be negative, like this product's okay, could have done better, but it's just okay. And then cheap, if I look in the dictionary, I kind of interpret it as like a flimsy product that breaks easily. But in this context, somebody wrote cheap, that was actually good. It was probably from price sensitivity. This product is cheap. I love being able to buy 10 of them. And then the other, Joel showed that grin example. This is something, I had never really done visual analysis, but with Data Robot made it super easy. But this could be done outside with all the general rules. But I love this for the explainability. In this case, it is this a dog or an object? And you classify, this is kind of funny. It's kind of gone around the internet. So I just kind of pulled up this data set. This is a loaf of bread. This is a sheepdog, a labradoodle, a mop. I think they have croissant somewhere. And then you can put a new face. You can put my face in, see if I look more like a dog, a mop, a poodle, or a croissant. But I love the explainability where it highlights what part of the image kind of gave it away. The teeth, for example, this is a muffin, but maybe the eyes were too far apart. This is fried chicken. But to make that even more clear, you turn off the color overlay. You can really see where were things thinking. This was a mop, maybe since it has a mop handle on it. So those are just kind of 2 examples of it. Image embedding, it's kind of unsupervised learning. It kind of clusters the images. It looks like labradoodles. I don't know if you saw Saruman, if you're a Lord of Rings fan, his hair does kind of look like these labradoodles. It's kind of fun. These muffins and chihuahuas kind of look similar. So I just thought that that's a fun example. There could be serious use cases. Is this a painting or not? Before you shoot a missile, is it a passenger airplane, or is it a cloud, or is it a nuclear missile? Things like that are more serious. Is this X-ray cancerous or non-cancerous? And then forward the likely ones to doctors. So those are some of the examples. And then, that's pretty much the presentation. You can scan these QR codes if you want to connect with us on LinkedIn. There are tons of use cases. If you want to go to pathfinder.com, see Data Robot in action. But yeah, we'd love to connect with anyone, have any follow-up. And with that, let me pass it back to Rama. see if you wanted to go to the networking part or if there's any, I don't see any more chat coming in, but thank you, Joel, for co-presenting, and thank you for listening to the audience.